Hello and welcome. So glad you were able to click that button and join me. 5.4 is all about integration formulas and something that we've already kind of discussed, the net change theorem. Now we're going to piggyback off of what we just went over and the fundamental theorem of calculus, knowing that now the derivative and antiderivative are indeed inverses and undo one another. But most importantly, how to find, that was part 2, the antiderivative from A to B in that area under the curve condensed down into this quick, easy version. And because we have that, now I'm going to give you a bunch of different rules or formulas for differentiation that we've talked about so far. And again, remember, we're just working these things derivative-wise. Chapters 3 and 4, it was left to right. Now with the integrals, antiderivative, we're now going right to left. Right, so looking at all of these, remember these are called indefinite integrals. When it is defined over some interval, a to b typically, then we will be evaluating. So when you see numbers, you should give and provide a number. That number representing the area under the curve from those two values. Where if you don't, then you are just providing the antiderivative for that constant k, or x to a power rule, or e to the x is just itself, because either way you go, derivative-wise or antiderivative-wise, you get the same thing. So when you don't see any values up there, you got to make sure that you put that possibility of having that C. All right, so if you want to pause it here and jot any of these down, take a screenshot, whatever, it's up to you. Make sure that you have all of these in your bag of tricks, because you should actually already have most of these. Some, the inverse trig functions, for example, those aren't some that we probably took the time to memorize. But all the other trig functions, the e, the 1 over x, x to a power, constants, those are all forms that we should already have and know. So as I mentioned, I want to make sure that you guys notice when you're finding the thing that has the plus c and when you're finding the actual area under the curve, where we use that fundamental theorem part 2. Right? Either way, it is finding the antiderivative of our original. We're going to call capital F of x. But if you have what is called an indefinite integral and you don't see those values a and b, then you're going to have to put the plus c possibility at the end. But if it's a definite integral, it's defined from some value to some value, then you will take the upper limit, we call it, and subtract it from the lower limit. And that provides us the area under the curve. So what other kinds of applications do we have using this fantastic fundamental theorem part 2? We already hinted at a few earlier in the chapter. They are called the net change, or the fancier way to say it is displacement, and the total distance. which if you recall, we spoke about this earlier as mentioned, but now we have the means to find them faster and easier. So the first theorem here, 5.41, is titled the net change theorem. And if we are going to find the net change, then we will take a derivative function and integrate it from some beginning place or time to an ending time. It is literally just our fundamental theorem part 2. What we are now just going to call a definite integral. All right, that's all the net change theorem is. Which is a generalization of this thing. And if you wanted to, of course, you could take any one of these, and let's take the positive one and add over the f of a to this thing and get just one of our changes. Just one of our values. Right now, of course, we can use this for the real world applications, which would instead look like what is called the net displacement. Now, what does displacement mean? If you were to take an object and displace it, that means you have moved it from its original position. And where it ended up is what we call the displacement. So to give you an idea, it's not the same as how far it traveled. But if we say went 7 units to the right, and then it went 4 left, and then you went 2 more to the right, you obviously can add all of that up and get the total distance. 7 and 4 is 11, plus 2 more is 13. But the displacement will only talk about from where it started and went right 7, then left 4, then right 2 more. You would have ended up at, if you went right 7, left 4, and then right 2 more, you can see there that we would have ended up at 7 minus 4 is 3, plus 2 more, we would have ended at a positive 5. So that's what we mean by displacement, where we said the total distance would have taken all of those values, the 7, the 4, and the 2, and got a total distance of 13 that we traveled. So a little bit different there. How does that apply to the calculus of all of this? Well, we're going to talk about a position of this thing then. And of course, if we're integrating, that means that they already are going to be giving us the derivative of the position, which hopefully you remember is a velocity, which we wrote as v of t. So if we were to integrate that v of t, it would give us our position function we called s of t. So if what we are going to do in order to find the net displacement is find that position function, which is integrating the velocity function from b or a to b, from A to B, then how would we find the total distance? Well, the difference is that it may stop and turn. And all of that is just going to take our two endpoints, where it started, where it ended, and that will give us our displacement. The difference from our beginning point to our ending point of our position. But if it did stop and turn and started here, came back, went forward, like we talked about with this little scenario up here, how are we going to find where it stops and turns? If we are given our velocity, then we should know that that means where our velocity will be equal to 0. And if you recall that we said we could split these integrals up and go from one value to another, and then add that to the same thing to get to our endpoint, then if we can find that place where it stops, then we'll be able to find the total distance that it traveled by adding those values. So the total distance, we want to know, as you should know, that distance is always positive, which is why we use the absolute values. We would then have to take that v of t and find where it's equal to 0. And then split this thing up by positives and negatives to then combat the negative by throwing an extra negative out in front to give us all of the positive values. That then would give us the total distance. And remember, there can be more than one places that it stops and turns. All right, so that's the big difference between total distance and the net displacement. Either way, they look very much the same, but you need to know how to get rid of the absolute values is by figuring out where it's equal to 0 and then combating any negative by throwing a negative out in front to ensure you get all positive values. That is why our distance had the absolute values around it, because we know that those are always positive. All right, there's one more topic within this before we get to practicing, and that is a couple of special cases. Namely, we mentioned this a long time ago. I don't know if you guys even remember. We talked about even functions versus odd functions. And when that special case of integration comes about, and they have us go from a negative a value to a positive a value. And if your functions are either even or odd, then you can get there more quickly than having to use the entire fundamental theorem part 2 in evaluating that definite integral. Do you guys recall what an even function looked like? And I don't mean just graphically, I also mean as a function algebraically, because we don't want to have to graph these to check. That's not going to do us any good to speed up this process. But hopefully you recall an even function would look like x squared, for example. And if I had x squared and I went from -1 to +1, and I'm trying to find the area under this curve to my x-axis, all of that well, rather than doing it from -a to a, hopefully you can see that this side would be the exact same as this side. So whenever we have an even function, we can do it quicker by just saying, you know what, let's only do half of this. But then we will go from 0 to a and just double it, as long as our function is what? Even. Pretty easy to remember. Even numbers are a multiple of 2. So you would have to double it and go from 0 to a as a shortcut. Why 0? When we plug in zeros, it wipes things out, so it should be a little bit faster than plugging in the negative a. 1, 2, 3, whatever it might be. But what about odd? What about an odd function? I'll give you a quick, basic, easy one, like y equals x to the first, or x cubed. And if I gave you x cubed as the graph, and again, I went from, say, -1 to 1. Remember, when we say area under the curve, we're talking about to the x-axis. So now I would be drawing this and that and finding these areas. But what's going to be true about this area? Well, it'll definitely be positive. And what's going to be true about this area, though? It's going to be negative. And because these are the same values, and this is an odd function, you're going to end up getting the exact same area here as you are here, but because one's above the x-axis and one's below, they will be the exact same values but opposite signs, which means what would our integral for an odd function from -a to a always be? That would be 0. Pretty awesome. That one is definitely faster than anything we could ever dream up. So these are two special circumstances that we will really look to see if there is an odd only when our interval is the same value on both the positive and negative sides. Let's define these. And just as a reminder, if you've forgotten how to check whether something is an even function or odd, we plug in a negative x into that function. And if it comes out the same, when you say the score is even, then that means it's the same. So even, same. But odd, you will get the opposite of what your original function was. And if that happens, then we can rewrite this as a big 0. Only if it's odd. But if it's even, then we said that we can rewrite it as the same function that we're dealing with, but if it's even, instead of going from negative a to a, we can go from 0 to a, just 1/2 of it, but we would have to double it since we're only finding half of what the original was. All right, so nice little shortcuts for us here, but this one, much nicer. This one, not necessary, but can help a little bit, especially if you got a pretty nasty function that you're trying to plug in a negative a to. 0 will work much nicer. So everything in this section that we've gone over very quickly, because it's really not anything new, it's just now we got that fundamental theorem part 2 that we can utilize to get these, whether they're special circumstances or applications, total distance or net displacement, whatever it might be, we can now use that fundamental theorem to speed up the process. And now we're looking for an even faster, quicker way to get through some of those, whether it's even or odd, from negative a to a. Right? Keep at it. We'll keep adding on more and more things to our tool belt, our repertoire, to expand our knowledge and our understanding of this last unit of study for Calc 1. Until the next one, take care, everybody.